Hi, everyone. Welcome to the Physionic Podcast. My name is Nicholas Verhoeven. I'm a PhD student in molecular medicine. I have my master's in exercise physiology. And today we're going to be discussing a topic that I've actually talked about quite a bit in the past, but I'm actually rehashing this or kind of going over it again, probably because I'm going to have to in the future many times. I'm currently writing a book on this topic, so I thought, why not put some content out related to muscle hypertrophy, muscle growth, and the three primary mechanisms as to how it's possible. So this is not going to be based off of any sort of particular review or any sort of scientific study. This is just the information that I've picked up over years of reading research. So we're going to kind of go into a semi-detailed dive into these three mechanisms. If you are watching the podcast, I will have a series of different images so you can actually see some of the things. I've created these images so that you can see some of the details of what I'm talking about, so you don't have to just rely on my descriptions. But if you are just listening, then don't worry. As always, I will be describing things to the best of my ability. Okay, so a bit of background. What is muscle hypertrophy? Muscle hypertrophy is hypertrophy. Hypertrophy is just larger muscles, the growth of the musculature. And obviously having larger muscles is strongly correlated, as a matter of fact, and I have content on this, with greater strength outcomes and generally better health outcomes. Of course, you might have to take people who take steroids out of that equation, but just generally having more muscle is a healthy state of being. So past models, something that you may have heard in the past, especially over the last, 15, 20 years, is that muscle damage is the reason why we have muscle growth. And that turns out to be potentially not entirely true, and that's why I wanted to discuss this particular topic, because there is more information that's come out. It's actually even something that I've said in the past, that muscle damage is the primary driver of muscle growth. However, of late, as more research has come out, there have been other factors that have sort of been implicated in muscle growth, which is really interesting because that actually offers us a good amount of reasoning for why we can build muscle in so many different rep ranges when you're exercising. Now, I'm not going to go into this too much, but there's also this debate between what's known as sarcoplasmic hypertrophy, sarcoplasmic growth, or myofibrillar hypertrophy. It's always tough to say myofibrillar. And myofibrillar is these contractile proteins that make up the muscle cells. So you have a bunch of proteins that connect with one another and latch onto one another, then unlatch and then kind of ratchet their way down the muscle cell, which ends up leading to this contraction. Now, if you have more of these proteins involved in the process, obviously you have a stronger muscle. Now, that will also lead to a larger muscle, but not potentially as much as something like sarcoplasmic hypertrophy. So sarcoplasmic hypertrophy would be a situation where you have the cytosol of the muscle cell. The cytosol I don't think they really call it this, but the sarcosol is another way of saying it, more muscle specific. So the inside of the actual cell itself also is called the cytosol. And that fluid, the cytoplasm, the fluid that's found in that area of the cell, is where you can get some level of growth. That growth actually comes across through things like glycogen. So the idea behind sarcoplasmic hypertrophy is that bodybuilders, this is typically associated with bodybuilders, that you see a lot more of this overall size increase, and that is driven by or at least partly driven by the increase in glycogen content that's found in the musculature, or it's a function of, as in the muscle grows, therefore it allows more glycogen in. And the reason for that is due to stretch. So if you have more glycogen that enters the muscle cell, or glucose that enters the muscle cell and is then stored, then that could ultimately then lead to stretching of the muscle cell. The reason being is that as glycogen is stored in the muscle cell, also water is stored. So you only have a finite amount of room within a muscle cell, so that means that it has to bow outwards. It has to stretch the cell. And we're going to see how that can downstream lead to cell growth. But again, I didn't want to focus too much on sarcoplasmic versus myofibrillar. That's something that I may discuss in the future. But now let me go ahead and jump into these three different mechanisms. The first mechanism, I'm just going to go ahead and discuss this one, is muscle damage, which is the one that a lot of people have focused on over the last several decades, many decades, because it is highly related to muscle growth, and which makes sense, because if you're going to be damaging the muscle, of course you have to go through a repair process, and then it made logical sense to then think that then you would be adding particular proteins as more protein synthesis occurs. So muscle damage is localized damage to different molecules within the cells, like damage to the sarcolemma, which is the cell membrane. Sarcolemma is just a fancier, a more specific term for cell membrane on the muscle cell specifically, but we'll just say cell membrane. So damage of the cell membrane, which is the overall kind of structure of the muscle cell, as well as the connective tissue that's around the muscle cell, so like the extracellular matrix that's found around that muscle cell to give it kind of connection to all the other muscle cells, and damage to contractile proteins. So a lot of this stuff is, if you're talking about like contractile proteins, it goes back to those proteins that I was talking about earlier, that the myofibrillar proteins, those are the same thing as the contractile proteins. The contractile proteins are made up of myosin and actin. And, well, those are the two primary ones, although there are many, many other ones as well that are involved. Like you've got the Z line, you've got the titin, and you've got a bunch of myosin binding proteins, and you've got a series of different proteins, but usually the two that people talk about is myosin and actin. So with this myosin and actin, as it interacts with, as let's say you're contracting, you're lifting a particular weight, that contraction requires X amount of connections of this myosin and actin connecting with one another. And as that occurs, you can get slippage, you can get breakage of those proteins, and that's the intramuscular, the within muscle damage that can occur. However, you can also have damage as the muscle cell overstretches or it flexes too much. Then the membrane gets squished together, or it gets stretched out extremely long because of the weight that's being applied at the very bottom of the movement. And you may have heard that something like eccentric damage or eccentric contractions, which are the lengthening of the musculature. So think of a bicep curl. At the very bottom of that curl causes the most amount of damage. And that's what people are talking about, because it's doing damage to that cell membrane as well as the connective tissues, et cetera, et cetera. And that's what ends up causing usually the greatest amount of delayed onset muscle soreness. So these deformations of the muscle cell internals as well as the cell membrane lead to a hypertrophic response. They lead to a muscle cell size increase. And that's through increases in protein synthesis and usually decreases in degradation, or at least at the very least, even if you have an increase in both, that protein synthesis overcomes degradation. So they're very highly related with one another. So the damage can, even though you're getting potential damage to the internals, the damage can actually be communicated outwards to the rest of the body. So let's say you have a really intense arm day, you're lifting for your biceps, you're trying to grow your biceps as much as possible. You're doing a lot of eccentric work, a lot of concentric work, and then there's signals that get released, and those signals, known as cytokines, are really just, there's a series of different signals, but some of them are cytokines. And those signals will then later on, they will recruit immune cells. And those immune cells are things like macrophages and neutrophils. And these macrophages and neutrophils will go to the site of damage, in this situation, your arms. And then there, they will start to release their own cytokines. And those cytokines can be growth factors, usually something like insulin-like growth factor. And that can bind the muscle cell and lead to more of that protein synthetic potential. So leading to more of that signaling to lead to overall protein synthesis. So we're talking about things like increasing the activity of mTOR, or mammalian target of rapamycin, which is a molecule within the muscle cell that stimulates growth. So as you have IGF that's released from the macrophages, you also have IGF that's actually released from the muscle cell itself. And those actions are actually called paracrine actions as well as autocrine actions. So autocrine, being like the muscle cell, will release IGF and will bind itself, essentially, or will bind other muscle cells in a paracrine action. So paracrine being kind of in the nearby vicinity. So other muscle cells are kind of communicating with one another, and they're also communicating with these macrophages. So the point being that you've got these immune cells that go into this area where there's so much muscle damage that they have to start cleaning up the process, and they start leading to increases in this release of these cytokines, these growth factors. And on top of that, you also have what's known as satellite cells, which are just cells that sit on top of the muscle cell, and they will donate themselves or donate parts of themselves to the muscle cell. And that allows the muscle cell to also grow more quickly in the future. As a matter of fact, I've wanted to release some content on this, and I might do that in the future. But one of the reasons why, if you take steroids and you grow to a certain size and then you stop taking steroids, one of the reasons why you can't ever say that you're now natural is because of these satellite cells. Because once they integrate into the muscle cell, they don't move back out. Once they nestle into that muscle cell, they can't get kicked back out. So that's a huge argument why a person who takes steroids can't ever technically be natural anymore. But that same process also occurs to people who just lift in general and build muscle. So these satellite cells will be activated by damage, and they'll also be activated by IGF. IGF will bind these satellite cells as well as other, what are known as myokines, other growth factors that will stimulate satellite cells to start to divide. So you get more of the satellite cells, and then the ones that do end up getting sort of convinced, they go into what's called a differentiation mode, where they then give themselves over to the muscle cell and become part of that muscle cell. So there's a lot more to that, but I don't want to bog down the podcast just discussing how satellite cells work. However, the difficulty of this, and the reason why there's been so much confusion related to muscle growth and its relation to muscle damage, and why people have confused muscle damage as this specific, is the reason why we get muscle growth, is because it's hard to tease out. It's hard to tease out these other two mechanisms from muscle damage. But over the years, especially recently, we've started to figure out that there may be other players. And it really, once I'm not going to talk about this on this podcast, but in the future, I'll be able to relate how the different forms of these signals, if it's muscle damage or the other two, how we can, if we understand those, we can actually use that knowledge to understand how muscle growth occurs in a series of different types of exercises. Different ways of exercising can yield the same result, which is something that a lot of people have fought over and tried to figure out for the longest time. But as we're figuring out the physiology and the molecular aspects, we're starting to be able to really tease that out. Okay, so the second one, and the one that I think is the most interesting, is the second mechanism is mechanical tension, or mechanosensation is another way of saying it. So mechanosensation is something that I've talked about at pretty good length in the past. I have content on it. It's definitely something that can be kind of confusing at times. Mainly what it is if we go back to our muscle cell, there are proteins that are found embedded in the membrane of the cell. And if you're just listening to the podcast, if you're having a hard time visualizing this, just hop on over to the video version of this podcast, because I do have visuals showing exactly what I'm talking about. So these proteins that are embedded in the membrane, they are separated, like physically separated from the molecule that it typically interacts with. So what happens is when we contract our musculature and that membrane slides together and kind of pushes together, then you have proteins like, I've said this is the main example I use, although again, there's others as well. Phospholipase. Phospholipase will interact because of this contraction, pulling the kind of deforming the membrane and kind of pushing the membrane together. I mean, think of like raising your arm in a dumbbell with a dumbbell for a bicep curl. You're flexing the muscle, and it's bunching together. That has to happen on a cellular level as well. So when that happens, phospholipase suddenly physically moves, even though it's anchored into the membrane, and interacts with phosphatidylcholine, which is the molecule that it interacts with. And once it interacts with that, then it does something to that molecule. It splits it. It splits it from a phosphatidylcholine. It splits it into a choline and a phosphatidic acid, which is another molecule. So now we have two molecules, phosphatidic acid and choline. And phosphatidic acid will then bind, again, this protein that I was talking to you about earlier with muscle damage, mTOR, which will then lead to more cell growth. So you're essentially translating mechanical tension and mechanotransduction, those are the same thing, is a translation of a physical phenomenon, you flexing your bicep, and then that then gets translated into a molecular signal, a chemical signal that then binds all these different molecules and ends up leading to a big change. Now, that also increases IGF levels. So just like muscle damage increases IGF levels, the mechanical tension or mechanotransduction also increases IGF levels. And as a matter of fact, independent of the immune response that you get with muscle damage, which is, I think, as far as we know so far, is specific to muscle damage, the mechanism by which you see increases in IGF are related to a different signaling cascade, a different molecular signaling cascade within the muscle cell. And that is mediated by calcium. So every time we contract our muscles, we release calcium within our muscle cells. So when that release of calcium occurs, and this actually also happens through channels that are found in the membrane, again, going back to the same cell membrane, when we contract our muscle cells, they have a sudden spurt of increase in calcium that's found inside the cell. And that calcium it will actually interact with other molecules, other proteins first, but eventually it interacts with a protein called calcineurin. Calcineurin activates another protein, which is a nuclear factor, meaning that it is a protein that will move from the cytosol, that area that I was talking about earlier, of the cell, and move into the nucleus. And then in the nucleus, where all of our DNA are kept, all of our genes are kept, that's where it will then bind to specific proteins, in this situation IGF genes, and lead to the upregulation of that IGF. So this transcription factor, known as NFAT, so nuclear factor of activated T cell, I'm assuming, I don't know this for a fact, but I'm assuming that they discovered this in T cells, which is an immune cell, obviously not a muscle cell. This NFAT is that nuclear factor that will move from the cytosol once it's activated by calcineurin, which is activated indirectly by calcium, and which is promoted by that contraction, will then lead to the increases in IGF. And I believe what I read just briefly is that if you if you cut out or somehow inactivate calcineurin, that then you inactivate the production of IGF by the muscle cells. So this is an incredibly critical situation. It's absolutely critical for this production of IGF. Now, that does not necessarily mean that IGF is necessary for the muscle growth process, but it may be a factor. How big of a factor is probably still to be figured out. Now, this mechanotransduction, going back to kind of the overall point, this mechanotransduction, if you remember that I mentioned the sarcoplasmic hypertrophy, sarcoplasmic growth, where you get buildup of glycogen, that is thought to be mediated through this mechanotransduction, because the more reps you're doing, let's say the more repetitions of, again, I always use a bicep curl because it's so easy to demonstrate. The more repetitions of this bicep curl that you're doing, let's say you're getting up to 14, 15, 16 repetitions, that ends up leading to a lot of blood flow into that area, but it also leads to the cell swelling overall. And that can be partly due to damage, but it's also due to this mechanotransduction because it increases the stretch. So cell swelling leads to increases in stretch, which then is also sensed by the muscle cell, which then leads to these cascades in these molecules. And these molecules also, one of them is a glycogen enzyme known as glycogen synthase. So glycogen synthase is the one that is part of that process for taking glucose molecules and turning into glycogen. So that is some evidence for this kind of sarcoplasmic hypertrophy that occurs. I think they're still trying to figure out how much of a factor it really is, but ultimately, as glycogen synthase levels increase, you get increases in glycogen content, and with increases in glycogen, you get increases in water content. With increases in water, you get more cell swelling, and that leads to then growth, the actual muscle cell growth as a result. So the point being that the muscle cell can identify other ways other than mechanical or other than muscle damage to lead to muscle growth. And mechanotransduction, mechanical tension is a huge one. Okay, and then the final one, which is something that we probably know the least amount about, is metabolic stress. You may have heard bodybuilders say, okay, well, maybe we need to feel the pump. That's what a lot of people like to focus on. Sometimes it just feels good, right? But it's also could potentially have an impact beyond just mechanotransduction, but potentially through metabolic stress. So metabolic stress being things that increase the amount of hydrogen ions, lactate, inorganic phosphates, creatine. All of those can trigger hypertrophy, muscle growth. So what is all of that? You might be asking. So when we're lifting weights, usually our cells are focusing a lot on glucose to produce energy, and that energy being ATP, adenosine triphosphate. I'm not going to go into all the metabolism of it, although I have been asked to cover kind of the metabolic switches and whatnot, which is an involved topic, and I'd be happy to discuss it sometime. But the point, just to limit this, glucose is in the bloodstream and it gets taken up by the muscle cell, or it can be taken from glycogen, which is that stored glucose I was talking to you about earlier. So if you break down that stored glucose, then you can have that available glucose for energy, and it goes through a process called glycolysis. So once it goes through glycolysis, I'm not going to go into the intricacies of it, but ultimately, because you are in a high intensity environment, you are trying to lift weights, a heavy weight, even if it's for 15 repetitions or 20 repetitions, whatever it is, it gets shuttled, and that glucose gets broken down and gets produced into lactate, really lactic acid, and then that lactic acid immediately dissociates into two molecules. So it goes from lactic acid and dissociates into lactate and hydrogen, more specifically protons, but we'll just call it hydrogen. So that hydrogen is what leads to an acidic environment. And that is where this metabolic stress idea is coming in, that they believe that there's a potential there that the increase in these hydrogens inside the cell due to this metabolism of glucose to lactate and hydrogen is causing more damage to the insides of the muscle cell. And maybe, who knows, maybe there are enzymes that specifically recognize the pH, which is the acidity. So if you've got low pH, you've got a high acidic environment. If you have a high pH, you have a low acidic environment. You have an alkaline environment. And the muscle cell operates optimally within a pretty strict range, pretty neutral range. I think it's like 7.45. So if you're lifting a lot, right? Let's say you're getting to that rep 12, and normally you get like 15, 16 reps. Your biceps starts to get really, it starts to burn a lot. Well, that's because you're creating this acidic environment that's occurring from lifting. So at this point, then, you're lifting this weight, you're building up hydrogens, which also don't just come from this glycogen being broken down or this glucose being broken down. They can actually also come from the actual contractions themselves. So as the muscle cell contracts, it uses ATP. Now that ATP, that adenosine triphosphate, the cellular energy within the cell, also produces hydrogens. So suddenly you have all these different systems that are producing hydrogen and lowering the pH of the cell. And that is, again, thought to create damage by damaging or kind of ripping and tearing apart at the proteins that are found within the muscle cell. So that ultimately then leads to overall muscle damage that is sort of independent of the muscle damage that occurs that we talked about earlier, just from having a heavy weight in general, just doing an eccentric motion and doing a concentric motion. So this can be an independent mechanism. And then there are also other ways that they believe, again, there isn't a whole lot of information on this yet, but there's also other situations where it's possible that the muscle cell is also recognizing the amount of other molecules, like the amount of creatine. If you are changing creatine from phosphocreatine, kind of its charged state, to its uncharged state, which is we'll just stick with that for the time being. If you have a rise in creatine levels, then that means you're using up a lot of creatine. Inorganic phosphates is another one. If you are cleaving that ATP molecule, you're producing more of these inorganic phosphates. So it's possible that the cell can also recognize that and have different proteins that recognize those different markers. Lactate, hydrogen, we talked about hydrogen reducing the pH of the cell, these different phosphates, and of course creatine, and others as well. I mean, a lot of this is very speculative, but ultimately it leads to greater degradation within the muscle cell, or you've got different enzymes that recognize these and then stimulate muscle growth. Okay, so I'll be honest, I covered about 2% of the information that truly is out there. But I don't want to walk away from this with just, just kind of hammering you with a bunch of information. So let's go ahead and cover the takeaway and kind of the big points, and then I will let you go. But there is, so far we know that even though in the past few decades we've said that muscle damage, and honestly, if you read a bunch of textbooks even now, and also even if you look at like YouTube videos and stuff like that, or just videos in general, you'll see that people always kind of remark about muscle damage being the driver of hypertrophy. And it is probably a factor, no doubt. We don't exactly know how much of a factor, but it is a factor. So there's more than one way that muscle cells are stimulated to grow, however, and it's likely in something like this order. So you've got muscle tension along with muscle damage, and then with some contribution potentially from metabolic stress. And muscle damage is still a likely player, but it isn't going to be the only driver like we once believed. And this is really going to ultimately open up how we go about training our musculature. We don't have to have this one size fits all, like, hey, if you're not doing this, then you're not optimizing your muscle growth. There may be a number of different ways that we can go about training to lead to greater increases in muscle growth. Okay, well, that is where I'll leave you. I certainly have a lot more to say on this topic, so I will definitely be releasing more content on this topic. But hopefully you got kind of just a basic overview, but maybe one layer deeper. And then we certainly have many, many layers beyond that. But I'll cover those in future content. Okay, well, with that, I appreciate you stopping by, and check out some of my other content if you'd like. I will link some of it if you're interested in this kind of stuff. And with that said, I wish you a wonderful day, and I will catch you in the next one. Have a good one, guys. See ya.